Hello everyone, this is Gourango Charan. I would like to present our paper, Computer Vision Aided Blockage Prediction in Real-World Millimeter Wave Deployments. This work is done under the supervision of Dr. Ahmed Al-Khatib. We are both associated with the Wireless Intelligence Lab at Arizona State University. This work is supported by the National Science Foundation. Future wireless networks should have the ability to satisfy the demands of several important applications, such as wireless virtual and augmented reality, autonomous driving, smart city, and Industry 4.0. To support these future applications, there are three main requirements: high data rate, ultra reliability, and extremely low latency. However, it is quite challenging to simultaneously meet these demands. Millimeter wave and sub-terahertz communications, with their large bandwidth, have the potential to support multi-gigabits per second communication. However, the wireless communication in this band faces several critical challenges. First, the high attenuation loss results in low receive signal-to-noise ratio. To overcome this challenge, we typically need to deploy large antenna arrays and use narrow directive beams at both the transmitter and the receiver. The other challenge stems from the sensitivity of the signals to link blockages. This motivates the millimeter wave and terahertz systems to rely mainly on line-of-sight connection. However, line-of-sight link blockages still remains a major challenge for these systems. In the event of a blockage, there will be a sudden disruption of the communication channel, severely impacting the reliability of the millimeter wave wireless network. Re-establishing the line-of-sight connection is usually done reactively, which results in excessive latency. Further, the high mobility of the user will require frequent handoffs, resulting in both reliability and latency concerns for the wireless communication systems. All this highly impact the ability to satisfy the ultra reliability and low latency requirement of several future applications. So, how to handle line-of-sight link blockages in millimeter wave and sub-terahertz networks? Several prior work have tried to overcome these challenges. An initial direction to handle blockages were centered around multi-connectivity, which relied on keeping the user simultaneously connected to multiple base stations. This was done to enhance the reliability of these systems. This approach, however, is inherently wasteful in terms of resource utilization. Further, it is normally reactive in nature. Another relevant direction in the literature tries to identify the blockage. The goal here is to differentiate between line-of-sight and non-line-of-sight links using wireless sensory data such as channel information and received power. However, similar to multi-cell measurement systems, the link identification approaches too are reactive in nature. More recently, work has been proposed for proactive blockage prediction. Here, a pre-blockage signature is extracted from the wireless signal, which is then further utilized to predict future blockages. However, the prediction window is very small, so there will be very limited time to take proactive measures. All these ideas are good, but have inherent limitations. In order to perform proactive blockage prediction or handoff, we believe that intelligent wireless systems are needed. We quantify such systems based on two parameters. The first is awareness, where the wireless network has to be aware of its surroundings and use that information to build the other important quality, which is proaction. This is where machine learning models and additional side information can be utilized to enable this awareness and proaction in the wireless communication systems. To do so, we first need to capture these features from the wireless environment. Sensing modalities such as vision, user position, LiDAR and radar can efficiently capture these features from the wireless environment. Developing efficient solution for sensing aided blockage prediction and accurately evaluating them requires the availability of a large-scale real-world dataset. With this motivation, we built the DeepSense 6G dataset. DeepSense 6G is the first large-scale real-world dataset with coexisting communication and multimodal sensory data such as vision, GPS data, LiDAR, and radar collected in realistic wireless environments. The goal of this dataset is to enable a wide range of applications in communications, sensing, and localization. The DeepSense dataset consists of multiple scenarios collected at different locations, different times of the day to incorporate diversity. The scenarios focus on different use cases such as vehicle to infrastructure communication, drone communication, reconfigurable intelligent surfaces, among others. The figure here shows a data collection testbed used in one of the scenarios. An important question that arises now is, why do we need multimodal data? In this work, we propose to utilize visual data to predict the optimal beam indices. This is primarily motivated by the low cost and ease of integration to the existing infrastructure. Further, the recent advancement in machine learning and computer vision has enabled new capabilities such as accurate object detection, image segmentation, to name a few. However, every sensing modality has its own limitations. For example, the visual or camera data is sensitive to lighting and weather conditions. All this highlights that unlike synthetic data, real data is not perfect. At any time t, given a sequence of r previous and current images of the wireless environment captured by the base station, the primary objective of this vision-aided blockage prediction task is to design a machine learning model that predicts the future link blockages. As shown in this figure, the machine learning model is expected to return the blockage status in the future k time slots. If there is any blockage during these slots, the blockage status for the future k time slots is considered as blocked. In this work, the value of r is set to be 8. That is, a sequence of 8 images are provided as an input to the machine learning model. In the next few slides, we present the proposed solution, development dataset used for evaluating the solution, and the blockage prediction performance achieved by the proposed approach. First, we will present the key idea and formulate the sensing-aided blockage prediction problem. In a wireless network, the link blockages are often caused by moving objects such as cars, trucks, buses, and humans present in the wireless environment. Given the dynamic nature of multiple moving objects in a real wireless scenario, the task of future blockage prediction becomes extremely challenging. The success of the dynamic blockage prediction task relies on characterizing the mobility patterns and geometric features of these objects. These additional indicators can only be obtained by observing a sequence of image samples. The primary objective of this task is to utilize the available sensory data and predict the future link blockages. For this, we define a prediction function psi theta that maps the input sensory data to the future link status. In this work, we adopt a machine learning model to learn this prediction function. The details of the ML solution is presented next. The proposed vision-aided blockage prediction task can be divided into 3 subtasks as follows. First is the image enhancement task. The second subtask deals with detecting the relevant objects of interest in the field of view of the base station. The objective of the third task is to predict the future blockages based on these extracted features. In the next few slides, we present each of the subtasks in details. Under low light conditions, the visual data turns out to be noisy and dark, making it unsuitable for further computer vision tasks. The figure shows some image samples captured under such low light condition. The vehicles are hardly visible, highlighting the challenges associated with such images. To develop robust solution, it is essential to perform some sort of image enhancement to extract the hidden details and make the low light images more usable. We adopt the state-of-the-art model developed for low light image enhancement. It is a fully convolutional architecture that learns an enriched set of features by combining contextual information from multiple scales. We observe that the image enhancement model has significantly improved the low light image samples. To detect the relevant objects of interest, we adopt the state-of-the-art yellow object detection model. In this work, instead of training the object detection model from scratch, we utilize the COCO pre-trained model as it is already capable of detecting most of the relevant objects present in the wireless environment. The output of this stage are the bounding box coordinates of the different objects in the environment. The final stage of the proposed solution utilizes recurrent neural networks to predict the future link blockages. In this work, we consider a two-stage gated recurrent unit followed by a fully connected layer acting as a classifier. In particular, this model receives a sequence of R extracted bounding box feature vectors as input and predicts the future link blockage status over a specific window. In this work, we utilize the DeepSense 6G testbed 3 for the data collection. The testbed consists of two stationary units. The transmitter is equipped with a 60 GHz quasi-omni antenna. The base station receiver has a 16-element 60 GHz phased array adopting a beamforming codebook with 64 beams. It is further equipped with an RGB camera that captures images of the wireless environment. The figure on the right shows the two different units of the data collection testbed. It highlights the different components of the transmitter and the base station acting as the receiver. The initial data collected using the testbed is referred to as the raw data. This raw data further undergoes a post-processing pipeline that involves data modality synchronization and filtering. We further manually generate the ground truth link status for each sample in the filtered dataset. The final development dataset is then utilized to train and evaluate the proposed vision-aided blockage prediction solution. To evaluate the efficacy of the proposed solution, we adopt scenarios 17 to 22 of the DeepSense 6G dataset. The scenario consists of diverse wireless and visual data collected during different times of the day. The resulting development dataset consists of around 39,000 samples. The data is further divided into training, validation, and test sets following a split of 70, 20, and 10. There are a total of 6 scenarios. The exact split in each scenario is shown in this table. We first evaluate the blockage prediction accuracy of the proposed sensing-aided solution. This figure shows the F1 score achieved for each of the 6 scenarios. Here, we have trained and evaluated the proposed solution on each individual scenario data. The proposed solution achieves an F1 score of 0.9 for the Future 1 and Future 5 predictions, highlighting the efficacy of the proposed vision-aided blockage prediction approach. Next, we construct a combined dataset by combining the training, validation, and test sequences of the individual scenarios. This increases the size and diversity of the dataset. We observe that combining the dataset helps in improving the model performance and is generally achieving better than the models trained on the individual scenario datasets. Next, we try to figure how early we can predict the blockages. To answer this question, we evaluated the top 1 accuracies and the F1 score for different future prediction window lengths. The proposed approach achieves more than 90% prediction accuracy till the Future 5 prediction interval. That is, it can predict blockages 600 milliseconds ahead with 90% accuracy. Accuracy being a holistic metric may not reflect the intricacies of the future blockage prediction task. To develop a deeper insight into the model's performance, we plot the confusion matrices for Future 1, Future 5, and Future 10 prediction window lengths. We observe that the proposed solution achieves a precision score of almost 96% for the Future 1 prediction window. Further, for the far more challenging Future 10 predictions, the proposed solution can predict blockages with almost 80% precision, highlighting the high efficiency of the proposed architecture. With this kind of interesting results, I would like to summarize by highlighting the 3 main points. The first is, we believe that proaction and awareness are great enablers for future wireless networks. Deep learning and visual data combined can get us close to that full proaction and awareness required to meet the high reliability and low latency requirements of future wireless communication applications. The capability of future blockage predictions provides an opportunity to extend this solution further and perform proactive handoff in the event of future blockages. Further, to overcome the inherent limitations of these sensing modalities, an interesting future direction can be to explore multimodal data fusion. Thank you very much for watching. If you have any questions, please feel free to get in touch with us.